Hello, everybody. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device, here to talk about pre-existing Alzheimer's neuroimages and QML, quantum machine learning prediction. Now, with this, I want to start off with driving forces behind quantum in healthcare. There's been a number of developments over recent months, and the number one, many people know. So, first quantum computer in healthcare installation has begun, anticipating finishing, basically early next year in 2023. They have a 10-year partnership, and this includes other types of emerging technologies, but, everybody's kind of excited about the quantum. So basically, as more people file in here, so NYU Langone Hospital #2 Fermi Labs is basically they're building their own quantum computer quantum sensors for MRI analysis. And this is a huge thing because this is just, we don't know exactly, or I don't know exactly that they're doing at Cleveland Clinic, but this in specific is to get better imaging, medical imaging off of people and we know this. Number three, so in cybersecurity, Sandbox AQ, Mount Sinai Hospital. So both NYU Langone and Mount Sinai are located in the state of New York. And then the National Science Foundation, basically in a couple months, it could be January, we don't know, but this practical quantum computer in 2023. Now, I took a further look into all these healthcare companies, and basically, there's a lot in drug discovery. As you may know, and the same thing with neuroimaging, is we're not going to be able to do everything we want in neuroimaging with quantum machine learning right away. But say, for instance, in these, protein cure, HQS, Polaris QV, algorithmic, is that it's pretty much in talking to one of the CEOs and watching one of these other broadcasts. Basically, there's approximations that have to occur in order to get somewhere. Now, that doesn't necessarily mean you can't have a usable product or service or software. It just means that, we don't have a million qubits that don't have error. We're still kind of at that stage where you have to find very specific things in quantum to get that advantage out of in hardware simulation. So I'm going to be going over a little bit of the regulatory insights, some more from last week. The crux of all this is stage one and Chemical Q Device with pre-existing images, and then some 101s on that, and then a paper, and then more of stage two detail for Chemical Q Device. Now, I went over this last week, and I wanted to touch base. So IEEE Quantum, basically, they do, so IEEE is associated with standards. So you have, these 9 quantum standards. I also found that back in 2020, and actually a member or a speaker on this discussion, he was a part of it, or this individual was, and ISO and IEC has already taken steps to consider all of these things. That was back in the pandemic, so there's actually a bunch of Zoom pictures of it all. So there has been developments with quantum standards. The ones that most, and you can see the ones at the bottom here, especially IEC, NEMA's electric enclosures, is FDA, I don't think, is really going to be in the business, Food and Drug Administration, of regulating specifics on hardware. I think the standards are going to be, approved by these other governing bodies, and then you're going to start to see in FDA submissions. You're required to meet those standards. So basically, if you're not familiar with this term, MAYA, most advanced yet acceptable, is basically any type of new technology. If you change too much at the same time, things never work out. So I'm projecting that to be a similar case. So in quantum machine learning with something called transfer learning, where it's basically fine tuning with quantum. I think that's where you're going to see your initial kind of forays into medical. And then they use this term a lot. Probable benefit is greater than probable risk. So in specific, it's not quite at that point where you can say we have a predicate device, our technology is a little bit different, but here's X, Y, and Z why you should use it if it's for quantum simulator, for instance, for quantum machine learning, or if it's a quantum computer that people can agree on. And I think the agreement will come more with your IEC and IEEE quantum, the other organizations, and FDA basically saying that you have to have this, before continuing. Now, number three, substantially equivalent to predicate device, this is a huge concept. Basically, you can have different technological characteristics, but they cannot raise different questions of safety and effectiveness to the patient. So in evaluating in all these things, most of us just look at quantum computers, quantum, qubits and error. And then, what's going to be under the microscope is how does that relate to patient safety and all this? And here's a potential scenario with IEEE quantum. And like I said, IEC and ISO have already made considerations, for the quantum technology. It is a developing technology. And then, basically, we're talking different hardware, software kind of applications for this. So here's a better layout. This is a condensed view from last week. So basically what Chemical Q device is looking at is using existing neuroimages, getting better prediction off these. So basically a lot of things in quantum machine learning can be done, bumping up to, quantum machine learning. And then, like I said, I've actually, there's a paper out there that does, quantum transfer learning. So these things are being looked at. And stage two, I'll highlight at the end. Stage three is basically a combination of the first two stages. Stage four is for FDA submissions. Important milestones include having collaborators, partners. That's basically a key aspect I'm looking at right now, as far as talking to either QML experts. There's a Alzheimer's expert, and then obviously a space and a building to do all these things. Now, FDA explains all this as you need to have organizational excellence. So that's program performance, governance, and operational efficiency in order to even be considered for submission for FDA. So a well-functioning company. So this is a kind of like it all spelled out between stage one, stage two, stage three. I'm not going to spend a whole lot of time on it. I'll spend time on stage two a little bit later in the discussion, but basically figure kind of this commensurate growth with synergy between stage one and two. So the Alzheimer's Disease Neuroimaging Initiative is pretty well known, and basically it's advanced over the years. So, pretty much you can't do really any of the in-depth detail with CT. It's too crude. It uses X-rays. Now, MRIs, just a standard MRI, won't necessarily cut it as much as far as like the emerging research. And it's more the PET, the positron emission tomography. So PET scans, people have heard of. Basically, the most common is for glucose metabolism in the brain. So you have a radio tracer that somebody takes, and then it shows up. So the more recent one is, PET amyloid. So this is amyloid beta plaque. I'll show you at the end, the mechanism. And then you also have PET. Tau PET is the one that's coming up right now. So this is how they laid out. So it's all based on funding, right? ADNI 1, ADNI Go, and then ADNI 3. And that's the promise is basically with Tau PET right now, where this goes. But, they have these databases that if you're approved, and most people I do believe do get approved, is that you could do research that, so say for instance, for Chemical Q device, that these are pre-existing images, and then all of a sudden, incorporating different types of quantum technologies, looking at them a different way. So the second paper basically is a 2019 imaging, so neuroimaging and Alzheimer's. It's a good 101. Okay, so Some of these things I've already mentioned before, but there's certain things that you can rely on, like the crude stuff, tumors, and just a standard MRI, CT scan usually will cut it. Um, and as you see with CT, hemorrhage, these types of things, but everything's going towards PET. It looks like, and in specific, I'll show you the pictures of brains. So what happens is you're losing tissue, and then you're filling up with the cerebrospinal fluid. So it's a material balance. You're not just the tissue doesn't go anywhere. Is that the solid is going into what it appears to liquid. So in specific, there's been different approvals, and especially with insurance, things have been developing over the time. To say like tau PET, like 5 years ago, I don't think was covered by most insurance companies. So you really have to prove this case. So for instance, FDA approved FDG PET for differentiation of AD from frontotemporal dementia. So this is more like, so the FDG PET is for glucose monitoring, where you put fluorine substituted compound into the brain. So here's what I was talking about. So on the top row is a healthy individual. So it happens to everybody, right? It's the same thing with the body breaking down with muscles. Is the brain just tends to atrophy. So in the bottom right-hand corner is the cerebral spinal fluid that you could see that the tissue, I believe the tissue is going into to make more of the cerebral spinal fluid. And you could take class. I've taken a class on neurochemistry. I've taken a class on neuroanatomy, and it's just good to understand these fundamentals. So this is another fundamental paper too. And the terms with these, when you talk about medical image processing or any type of image processing, they can refer to post-processing as a later steps in image processing. Now, I've always been sharing, and I'll show you a little bit later, one that breaks it down between image formation and image computing. But basically, anything that's like detection or reconstructing is more your image formation. Now, they say 5 different classes of image processing algorithms. Keep in mind, this paper is it's a little bit old, but it's very thorough. Image restoration, image analysis, image synthesis, image enhancement, and image compression. In specific, they used to use this just like how we use film cameras. I mean, not just like that, but it's film. And it has issues if you're just off with the radiation. Obviously, too much radiation is not good for the patient, and too little, things just don't show up well at all. So there's inherent advantages in this digital world, but we shouldn't take it for granted that everything is better. They actually say spatial resolution, and figure like your old movies, say from like the 70s and 80s, they were shot in 16 by 9. And then, the HD upgrade to it looked better than, say, for instance, like your 90s or, 2000s, kind of like sitcoms in 4:3 and digital. So yeah, typically it's a lot harder to work with film, and that's the whole thing. It's so much more versatile. But keep in mind, better spatial. I don't know if that'll always be the case, but that's one of the highlights they had for it. So these are just some of the techniques you can do. So in all these, you consider most of it. I imagine it's a doctor sitting at their workstation, and they just want to see better, right? Like they want to see what's going on. And so you have all these techniques in order to get a better diagnosis for the patient. And keep in mind, this was done on Photoshop for a while, and I, further investigated this, and now it's medical specific software that does a lot of these techniques. Now, Caltech and NASA are known as like some of the these pioneers in these developments of image processing. And there's, I don't know if you've come across in your other studies Fourier transform. So it's moving between time and frequency domain. So in CT, the cruder kind of X-ray to take a neuroimage, spatial location domain, and an MRI is spatial frequency domain, and then it has to get converted. And Here's the steps laid out. So basically, the thing with a lot of these things is like if it gets better diagnosis, I don't know as far as like if you sell things specific that for these cases or if it's just done by the doctor. So image restoration improves distortions or degradation, analysis, measurements, and statistics. Segmentation, I'm going to be talking more on that. Feature extraction and classification. Synthesis, combining images, enhancement, edge enhancement, spatial and frequency filtering, image combining, noise reduction, and compression is kind of like that. If you get into lossy compression that is dramatically reducing file sizes, it may inherently take out some of the image that the doctor wants, so they don't like the liability of, extremely lossy formats. So I thought this is very interesting, and this is just one of the things. And there's many, many like pictures in this paper. You have an original CT image with a filter, and it creates blurred. So that's the top row. Now the bottom row has the original image again, and then you're subtracting this blurred image for an even sharper image. And this is just basically a foray into all the different tricks of the trade of getting better images. And in this case, and it's a little bit older paper, it does seem like that there is an inherent benefit of doing that specific technique. So you're talking image enhancement, image compression. So I talked a little about compression. And then, this paper is basically just getting into this, but somebody just, somebody messaged like, are you using DICOM? It's a pretty big thing these days. And then we have HDR on our camera. So that was like a 101. And all of these embedded in the PowerPoint are basically in-text citations. So, you can check out any of these papers. So this paper was very interesting. It kind of took me by surprise a little bit, just because the amount of research that was done with it. So basically, you're talking about convolutional neural networks and PET scans, early stage Alzheimer's disease categorization, and basically their findings. It's easy. So AD stands for Alzheimer's disease, and then NC is normal control. And then your MCI is mild cognitive impairment. So they always say that Alzheimer's is a multi-class thing. So so even though you can get a high number, it's easy to compare between Alzheimer's disease and a normal control. That's why that number is 89% at the bottom. And then the 59% is 3 classes. And then it's basically saying, this technique that they use, is better. I'll show you the chart for it. Now, this is everything kind of set up. So this is multi-class, and then the one on the top is for 2D, and then the one on the bottom is 3-dimensional. So you have all of this, and then, like I said, this paper, it was a lot of work to it. And then basically you can augment data, improve it or boost it, image cropping, resizing, shifting, blurring. And then in specific, and this is how I talked about before with transfer learning, is to achieve effective performances on different tasks. So you have 2 different types of transfer learning, cross-modal and cross-domain transfer learning. So like I said, many of the quantum, these initial papers out are using some form of transfer learning, i.e. fine-tuning and keeping a lot of the original the same and fine-tuning at the end. Now, the whole goal is you don't want bias. And then in specific, they talked about their studies did not have the cross-modal data sets. So that's one of the transfer learning ones they didn't have. And then here's where quantum could be inserted in the future. So when they're talking about hyperparameters, is that it's such a computational demanding thing. And again, quantum computers won't solve every certain task, but that might be an area. So here's the results again. So 89% for the Alzheimer's disease normal control, i.e. it's pretty easy to tell the difference between a healthy patient and Alzheimer's. And then it's harder and harder, especially between, normal control and MCI. And then you also see Alzheimer's disease and MCI. So the numbers lower there, but better than some of their competitors. So the future studies, they want to employ graph convolutional networks. And I was surprised they wanted to employ generative adversarial networks. So GANs, it's been talked about in this discussion, but basically this is taking, say, 90% noise, just random noise, with 10% real images, and in an iterative fashion, you're generating images that look like the original images, the real images. So obviously it's taking a while to get into medical, but that doesn't stop people from researching it. So here's the results. So basically the 3D CNN, so you'll see these are PET. So basically getting better results with PET versus MRI, I guess is a big key. And so there's that 89% for AD-NC for the proposed approach. And then you see at the bottom, this 59% for the AD-NC-MCI multi-class. But it stacks up against other competitors. Basically, that's it, is you want to, replicate what a doctor would see in their office. So this paper in specific, so this is an INQ paper. So I would recommend taking a look at it. And as with anything, the hardest thing to determine is what was the best part of the computer, what was the simulator. Now, I think with this specific paper, they found that, it's basically upping the difficulty of the task, and then the results of the computer, the quantum computer, were equivalent to the simulator. So depending on the difficulty, that can be viewed as a good thing, right? Like positive steps for the quantum hardware. So we're talking about, it's using ion trap. It has flexible qubit arrays, unlike gate-based superconducting, and then quantum computing language. So this was specifically for polymer properties, and I kind of, focused on the basics of it. And here's some basic graphs. Now, in a lot of these things with the hardware, it's too expensive and it takes too long. So there's an approximations that are made. So the column on the right with these graphs, obviously the more shots, the better. And your R squared, you don't want it negative. So it does say negative 0.07. But it's interesting in these papers because it says, for this specific case, classical, there's this specific aspect of it, it's better with classical, and other reasons, why it made sense to, do hardware. So basically it's called the stochastic effect, investigating the level of noise generated in a real quantum computer on model learning. And then the simulator that they used was this blue cut. So I think it's the most recent of the quantum machine learning articles in Nature. So this is a Nature paper here. So this paper, Quantum Machine Learning and the Power of Data, is this Google paper. The big thing with this is it's engineered data, it's not natural data. And I'll show you in a chart coming here. But to get their good results, they had to use, data that they made up. So basically, you're talking about these geometric constants. This is basically like just framework that they're laying down for the terminology, geometric construction. And you'll see quantum kernels a lot, empirical learning advantage for quantum models. Now keep in mind, because of the hardware, there's limited things that you keep seeing all the time, and quantum kernels is one of them. Now, here's the data. So it's a problem engineered to maximize the potential for learning advantage in a quantum model. Now, this is a 2021. And then in specific, you can see the blues, the quantum kernels outperformed. But that's the whole thing, right? Like, you want to use natural data, but it's engineered. But it's a proof of concept. And I'd say at that time, it was definitely ahead of its time. Now, in this specific paper, this is a 2021 quantum machine learning advantage. So power of data and quantum machine learning is the name of it. And I would check this out if you're looking to program. If you remember me talking about the Los Alamos National Laboratory paper, previously in previous discussions, that's a little bit more mainstream. Now, this one's a little bit more, the technical nuts and bolts. But I do think it's interesting because you'll hear this from other people too. Improve the purpose of using QML is either to improve the training process of existing classical models or enhance inference in graphical models, and then in specific kernel methods. Now, this is actually there's two of these paper. The Google blogs tend to be an easy and like summary of basically other papers. I think this is a different paper though. So kernel methods provides provable guarantees and are flexible in the functions they can learn. So as you can see, so a lot of this is basically like, if you don't understand quantum machine learning and you're designing new tasks, and especially as the hardware gets better, these fundamental papers, this is one of them. They call it like a training guide or something like that. It's kind of like, what you really want to see is basically don't waste your time on things that don't really don't have a high potential for quantum advantage over classical. So this geometric difference, so you've heard of those two other geometric terms, is the closest efficient classical ML model. And you want a big gap, with all of these. So the larger geometry gap, the larger prediction advantage with quantum machine learning. Now, they say this is the first empirical demonstration, and again, this is 21 paper, of a large separation between quantum and classical machine learning models with prediction error. And then in future studies, they want to identify embeddings that are hard to approximate classically, and then exhibit meaningful studies signal on local observables for very large numbers of qubits. So some of these I've gone over a little bit. So these are, I call these the Impact Healthcare 2021, 2022. Actually, it's a revised slide. So basically Amgen, IBM, IEEE, you'll hear things like empirical quantum advantage. You'll hear things like, one of the biggest quantum machine learning studies out there, if not the biggest. The Roche QC, where is basically for medical image classification. And then these other COVID papers, cognitive computation, NIH, BMC, Springer Nature, basically we're not there yet as far as having clinical use, but basically, some good motions going through with some of the bigger companies. So this is a new slide I put together. So it summarizes other things that I've talked about. So Los Alamos National Laboratory, they kept saying sample complexity instead of time complexity. Go after those problems for early quantum machine learning advantage. And then hidden parameter extraction, they also mentioned as well. Now, with all these things, especially Los Alamos National Lab, you have your best chance of quantum advantage as you incorporate more quantum technologies into it. So when you have quantum memory, quantum sensors, quantum data. Now that the second paper here, is the Google, Caltech, Harvard, and this is the whole, they used the previous, Sycamore processor from 2019, and with quantum sensing and quantum memory, overcoming the limitations of the error so that the error was no longer the principal component. Keep in mind, we don't want error around, but at that same time, there's things to be learned from all these papers. So even for, residual error, with and you have, say for instance, this quantum sensing memory combo, and then doing entanglement and storing, before the error, you basically is such a huge thing. So here's the number 3. I covered this: large geometry differences over classical machine learning model for data set that exhibits large prediction advantage. I've covered this earlier. And then this last one is the IonQ, basically saying if you have the ion trap technology, flexible model construction, for that specific application. Now, here's the big table of quantum artificial intelligence. This is what kind of kicked off a lot of this. They actually call this the quantum machine learning table back in 2017. And then in 1994, there was the beginnings of a lot of this. So in the upper right-hand corner, you have combinations. You can be with data, quantum, or classical, and then with algorithms, you could be classical, quantum. So you have those 4 combinations. So you see most of these. In this slide, the table is like 2.5 pages long, is QC with that. So that would be, quantum data and then classical algorithm in that specific case. So I went through and kind of like refined a lot of these. So basically, the big papers are the ones that sticks out, the IBM, Amgen, IEEE, but these are recent healthcare hybrid QML articles. And again, the references are embedded into the PowerPoint, but you'll see a number of COVID applications where they were trying to get this out, using quantum technologies. I don't know what the limiting factor was, probably the hardware and noise. And here's additional resources, and then I'll go over this and other things too, but these are just 3 good, spreadsheets to get you situated in this quantum arena. Now, the background with this is basically, local minimums and barren plateaus exist. As you increase in qubits, your barren plateaus, or you want wide, they become narrower, is inherent. So there's things that's fighting against. And then I guess in 2023, it's finding the sweet spot. Like if IonQ and Dell have this partnership, and I've talked to a number of the hardware manufacturers, and then, how much of it is simulated, how much of it is other technology. That's the hard part to figure out. I guess you just have to run like on AWS Briquette. But the big thing is, 76% of HPC data centers to use quantum, and then IBM, they're capable superconducting with 433 qubits, and then modular up to 16,000 towards the end of next year. So these are additional things as far as what's been done to help QML, anywhere from, it is the most common application for quantum computing, all the way down to, President Biden, President Obama supporting that technology, to at the bottom of BCG's $850 billion annual. I think it's worth by 2040, but there's huge numbers. And obviously we had $3.2 billion private investments for last year. Now, I wanted to take a look at these. So these are interesting. So for those that don't know, IBM sold their healthcare division to a company called Meritus. So they do mention quantum computing that they're looking at. So they're huge. They, likely doing a lot of the things I'm talking about. So it's interesting. And then especially some of these other ones are very specific to, stroke is more brain. The AI doc on the upper right is more, it's a comprehensive package for diagnostics, consultation, treatment. So I don't necessarily think looking at things more fundamentally like chemical Q device does, as far as, better prediction of the existing images or even better images. Now, Zebra, it's that same Zebra we know, but digitized radiology scans for diagnosis a lot, and then Viz AI in the middle accelerates care coordination. There's a lot of these things to make it easier on the doctors, so say these kind of like, and Sirona is another one of them, radiology OS platform, specifically for the doctors. But then you'll hear a lot about this analytic, combines processing systems and data. So a lot of these that I'm going over are more like, well, denoising for low count images is more like on that fundamental level. And then Huron on the bottom right automatically quantifies multi-tracer bindings. So I believe that's for PET. Now, I've shared this slide before, and I'm just completely like, it's this analog device that's on their website. And again, you can click on the number for their site. And then, so this first part, image formation, is detection, sensing, and then you have reconstruction algorithms you hear about a lot. And then the next is image computing. And I think these terms, post-processing image computing, are used somewhat synonymously. So you have enhancement, analysis, visualization, management. So this kind of gives you that framework for the next slide where things are fitting in here. So in data acquisition, this goes back, several presentations ago, is quantum sensing, right? So there's all these, especially in diamond quantum sensors. So, and again, all this is for stage 2 for better neuroimages, a little bit further down the road. And, there's quantum ghost imaging, quantum image processing. So basically, this is at the raw data level, and then reconstruction. The ones that I have italicized are, there's a big paper. MIT had a huge conference, and then they took, I don't know, 6 or 9 months, and then they published a paper on it. And some of these are from that presentation, basically with an existing ML approaches with data-driven learning, accelerated reconstruction, motion correction, MRI denoising. So if you think of basically machine learning and quantum machine learning being somewhat interchangeable or compatible, then you can see by this, what areas to you can go into with quantum. So enhancement, this is, I think, more of like the time to frequency domain, that kind of stuff. I haven't come across that much as far as the quantum research or machine learning. And in analysis, you'll hear a lot about, segmentation. So 99 through 104 in there are basically ML approaches to segment the whole brain. Visualization, something the startup probably won't focus on. So these are platforms like FiberWeb, XTK, Neurolines, and then brain atlases are different. But basically, expect to see, especially if the ball really starts to roll, updates to those, platforms. Now, management, obviously sending patient data over today's internet. I think there's been a number of studies that say, like, we can do it safer using post-quantum cryptography, or we could do it faster, so the doctor doesn't have to wait, or say, for instance, what we just covered, you don't have to compress as much, those types of things. And then I put below here additional growth areas. So when people hear me talk about all this stuff, is basically we've gotten so crafty in the techniques because the hardware has not been awesome yet. So people optimize quantum circuits, that's an option. Quantum GANs, so basically if you're limited on medical data, and then it's okay, to use this artificially trained data. Radiomics is a huge thing too. I haven't, taken a super close look at that, but basically, it spells prediction. It's a very interesting approach to take a look at. Obviously, additional quantum algorithm research. Now, at the end, you might see a quantum federated learning, actually in principle, right? And again, if you look at today's national quantum internets or the plans for it on these sites, even by government sites, they're hybrids, right? So you still have classical parts, and you still have you have these new emerging quantum parts. Now, I like this article, technology readiness levels. So it's basically a super thorough thing when you're shipping something something to the moon. It just has to work, right? So there's 10 different levels. It's 0 through 9. So in specific, this is a proposal to say this could be for stage 1 or 2 or even both of a super thorough approach to making sure your quantum machine learning algorithm, it's going to do okay in the long run. Now, the chemical Q device mission statement is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and a resolution combined with advanced prediction and neuroradiologies for Alzheimer's disease. This includes quantum sensing algorithms, possibilities, MRI, PET, CT, and then in specific at the bottom, the global AI and medical imaging market is expected to grow at a compound annual growth rate of 45%. During the forecast period 2022 through 2027, neurology has accounted for the dominating share in the industry. So I haven't come across too many other, startups or companies, obviously the IBM, the new company Meritum that they formed. But you'll see a lot in drug discovery, and their compounding annual growth rate may be, on average 36%. So, that doesn't mean everything, but just a good ballpark. So all these decks are available. So this is 6, 5, so 11 in specific with neuroimaging, Alzheimer's, quantum machine learning, these types of things. And then, so I talked about this earlier, but basically the current neuroimaging approach is this tau PET, positron emission tomography. And, basically to look at, tau PET instead of amyloid PET or FDG PET, those types of things. But it's an ever evolving technology or science, basically. Here's additional things to see on Neuroscience News. They publish almost every day, it seems like. They have a good stream of articles. And then here's a lot of the nonprofits have been associated with San Diego Alzheimer's Association as a volunteer. It's a very real thing when you talk to people as far as caretakers, the amount of involvement that's required, for an elderly, greater alleviation of that would definitely help. So this one, is basically, I asked around and then I couldn't find it, so I just made it. So IonQ, Quantinuum are both ion trap, IBM and Google are gate-based superconducting qubits. And these are what I hear the most. And then in specific, as you can see, they vary by qubits. The one that I'm most interested in personally is the Dell IonQ. And you can see they say their coherence time is the longest. Now, Quantinuum, I think over half of their employees are PhDs, like researchers. And then so they come up with these interesting things like qubit recycling. So 80 qubits circuit is run on a 20 qubit processor. And then IBM takes the bulk of the news. So this is theoretically the most powerful technology. Now, it's still kind of limited by the nearest neighbor in certain applications, but when I talk to some of the manufacturers, they say sometimes, depending on the application, they'll use ion trap, and then other times they'll use gate-based superconducting qubits. And then, keep in mind with IBM, the biggest thing, I think they said 2 to 3x times better coherence in their dynamic circuits. I'll go over kind of error correction a little bit more. And the one on the right with Google is basically, they use this old quantum computer, the Sycamore, and they haven't announced any new hardware, so they have to be up to something. And anyway, they've been coming up with I've shared 2 of their quantum machine learning posts, and they've been in other big papers too. So it's interesting, right? They're the first to get quantum advantage, and using quantum sensing and quantum memory, kind of mitigating that. I also include at the bottom, so spin qubits, photonics, neutral atom. I'm still, and we could have a discussion on this afterwards, as far as, are these all equally gate-based computers? Because I've only found recent papers on kind of the gate-based with photonics and say the neutral atom. So this paper I would definitely check out. It's Wang HL et al. And it's close to 500 references. Quantum error correction is one of them. And this, because just coming from IBM News, we'll hear about dynamic decoupling is in here. And then when I saw this one, I was like, okay, close to 500 references. It's a Chinese-based paper. I'm like, okay, people are just not giving up on this, so even if we get, 5 nines, 0.99999 with a percent error, some of these technologies will still, like some of them will find use, in the future. But it's interesting because you can further research all this, but this paper kind of, it took me for surprise a little bit, just because it's an archive right now. So I'm interested as we go into the new holiday here. So should be able to come on if you want to. And then hopefully you're able to see some new stuff as the startup progresses here. And then, yeah, so basically anyone, so previously we have George and Ron, feel free to come on. Either or is fine. You can unmute or do your video. And then it's just that time of the year, huh? So a bunch of quantum hardware news in the past couple weeks with IBM. And then, more recently with the Dell IonQ. And then the biggest question is what does it all mean? And then, so Ron or Mary, did you have any questions or anything with quantum or medical? Go ahead, Ron.
Hey, Kevin. Missed you the last couple of times, so it's good to get back in here. Um, so, have you had any success with finding pre-existing data sets that can be used for research? You were talking more tonight about PET, so that would probably be an interesting area.
Yeah, I guess the two approaches. One of these papers that I mentioned here, one of the bigger one, I think it was the 3D convolutional neural net, like the multi-classification paper. I think they actually use ADNI, those data sets. And as far as I know, they're not too hard to get. For me personally, I would want to make sure that I'm all set up, before I start inquiring. There's other researchers. I talked to a gentleman. He's published on QML. It was more of like a QML healthcare review, and he does clinical research, with QML. So I don't know exactly what they're using, for their data.
And it seems like these types of images are going to be relatively large. So, are you going to be forced to access them in the cloud using cloud services for high performance computing and actually we're kind of stuck with that in terms of quantum stuff. But
Yeah, I can barely hear you, Ron.
hold on.
But yeah, it's worth taking a look at as far as number one compression, how much they're minimizing file sizes. And then I think so every say for instance when ADNI got started, I think around 2004, they gradually change, so if the big thing was just the FDG PET to amyloid PET, now it's the tau PET. And a PET image, I think, is more real time. It's not just structural. So, with that additive too, but basically, if you can make that case as new quantum technologies appear, say for instance, they connect DCQNet and Chicago, in Washington, DC, and then it's faster, more secure, the whole kind of thing. So that may happen because Chicago or DCQNet says we will have a national quantum internet. Now, one of these recent, I think it was 2 or 3 weeks ago, I shared an interesting thing, and it was basically, it showed the existing internet and the quantum internet with all the nodes and the repeaters. And it had kind of like the zoom in as far as like, this is what's happening, at this, say, section of the hybrid network, and then a zoom out as far as like controlling things with quantum computers and controlling things with classical computers, um, those types of things. So yes, yeah, the images are going to be large, and then I don't see us switching back to film, for many reasons, but it's on the grand scale that you could have quantum sensing technology that could start hinting more towards super resolution. It's fluorescence based, right? So measuring a rat's heart at millimeter instead of centimeter resolution, and now more to the extreme. But it's just interesting in how a lot of these technologies kind of interplay and how they'll all kind of work together.
Yeah, is this better?
Oh yeah, yeah.
Um, so that data set you were talking about, um, if you need the performance of the either Amazon or Google's web services, are they giving you some sort of size metrics on on these data sets as far as how much space you would need? I mean, anything you go and do in the cloud, you're paying for everything
Uh-huh.
as far as, and if you want persistent storage, it even gets a little more expensive. Um, it gets to the point where it's not even practical to start up in multiple instances in the cloud and then upload your data to it, because the data is really huge. You spend all your time uploading it and you're still paying these instances to sit there and just upload data.
Yeah. I mean,
And those,
I'm sure it's a valid concern. And I mean, for me, it sounds like a lot of these, that are kind of oh, leading the industries, it goes back to like the whole FDA kind of organizational excellence is like, no, you don't want to throw money away, but like, you understand what you do, and there's going to be these inherent costs along the way.
yeah, so then the other alternative is you build your own mini server farm, download the data, and do all the work locally.
Well,
Um,
that's what I was kind of thinking, because as far as like, say if they have 300 or 500 images, I'm not quite sure if you get it up front. And then George, if you have any additional insight too.
At certain scales, building your own can actually be cheaper than renting the cloud.
Uh-huh.
It depends on the use case. Where the cloud is best economically is for very elastic loads. But if you have static loads and a lot of storage, depending on the scale and your particular use case, a local data center or a co-location can be cheaper.
yeah, I mean, as far as the data size, that's not that difficult to build a local server with lots of drive space. I just saw a video on a guy who built a local machine out of Raspberry Pis that has like 2 terabytes of storage. So that's like 1,000 gigabyte drives. Um, and he's using hard drives. He's using the hard drives that are in the 8 to 12 gigabytes per unit. So that part's not the difficult part. If you get into the number crunching, then you start looking at graphics boards that are in the 1,500 to 2,500 or more dollars per board, depending on how much crunching you need, and how many boards you need, and how are those things coordinated with your storage and that sort of thing.
Yeah. It's interesting you mentioned that. Like when I first got really started on a lot of this, I always thought like a Raspberry Pi quantum computer would be kind of cool. Obviously it's not going to be awesome. When will we see it? Kind of thing. Like, and then has there actually been a lot of good innovation that's come out of Raspberry Pis, uh, just other than just cost?
Well, Raspberry Pis are tiny little computers. I don't know if you've ever seen one. I've got a whole bunch of them. I actually
Yes.
run one of my workstations off of a Pi 4, and I've got two 4K monitors plugged into it. It's crazy, and it's hardly bigger than, I hate to use this comparison. It's a pack of cigarettes. It was about the size of the thing. Um, but another thing that I heard about, I haven't checked it out, is somebody supposedly makes what they call a hat, which is an add-on board to a Raspberry Pi that has supposedly some sort of quantum-like circuits. I assume it's that chip that is in the Samsung. They put it on a hat board, and you can plug it into a Raspberry Pi and play with it. I think it's about $100. I was going to look into just seeing if I could get a sample of that chip from the manufacturer.
So again, what part of it is quantum?
It's the chip that's in the Samsung phone.
Oh, that's a quantum random number generator.
Yeah, but
Yeah, that's
so
just
that they
weird.
call it a quantum hat because it's got one of those chips on it. So
Oh, okay.
yeah, but
It's a,
as far as a pie size quantum device, yeah, it's gonna be a while.
yeah, because for those, oh, did you have something, George?
The limitation with Raspberry Pi and other single board computers isn't so much the CPU, it's the bandwidth between the CPU and memory. And
You know what'll fix that, right?
that you don't really have a backplane like you have in a larger motherboard-based computer.
Yeah. Now we've talked about this a little bit. I don't know if you're going to say this, Ron, but neuromorphic computing would fix that. I don't think it's cheap or readily available, but
But if you're
I haven't heard of that one, but to the point of putting Raspberry Pis together in clusters, there's people doing that. The Raspberry Pi has very fast access to its internal memory, but the statement is correct that uh, they all have what are called GPIO ports, and it's been considered that somebody could build a backplane that would connect those together, but unfortunately, the CPU they used left out some critical instructions for dealing with the GPIO, so it may not wind up to be as fast as it could be. But some of these clusters of pies, 1632 pies, and that they connect them over the gigabit port. And for number crunching, apparently that's not terrible. So again, this one guy with, I don't know how many Raspberry Pis he used, but he had a terabyte worth of hard drives that they were talking to
yeah.
and managing. So
Yeah, I mean, all this with the NVIDIA, because they have their own, it's called Q Quantum, CU, then Quantum, and then CODA, QODA. And they say more and more people are using it. And at that same time, when I looked at the Dell IonQ announcement, there's NVIDIA there too, as part of these, I think they're enterprise solutions with a little bit of quantum now.
the NVIDIA, I think, is a bit of hype. If you read the fine print, it's quantum ready.
yeah, NVIDIA is positioning to be the classic side of the hybrid for short term.
Yeah, and I guess
and they're going to win because their GPUs are just off the scale.
yeah,
So
and that's what it sounds like too. And with all this, it's just hybrids upon hybrids. No, for those that don't know neuromorphic computing, it's both processing and memory at the same spot. So it's called neuromorphic because that's how our brain works, right? Like our brain isn't as fast as a supercomputer, but the architecture is very favorable, for all these neural nets and deep learning, and that's where we're gaining all this insight from. So that's the thing, is basically I wouldn't be surprised for a quantum Raspberry Pi or something like that, not for security, but a little bit of the computing in these next coming years. And I was thinking that as far as sparking innovation, because that's what it sounds like with these original Pis, is that people do all these weird and crazy things for awesome results at a low cost, right?
Yeah, and if you want to go smaller than a Raspberry Pi, there's all kinds of new microcontrollers, like in the Arduino family and the ESP family and the what's the other one? STM family. These are crazy powerful little chips that are the size of your thumbnail. And and to George's point, if you could figure out a way to get them to communicate with each other at ultra high speed, you could take a little thumbnail chip, teach it how to be a neuron, and then just hook a whole bunch of these things up together in like a neural network.
I came across this very interesting. It was I was just searching for quotes on quantum machine learning for the newsletter, and this gentleman, I think he's PhD. He says with 12 qubits, QIDITS, you could simulate 100 billion neurons in the brain. Are you familiar with the QDIT, Ron?
Q dots or
No,
Q
it's QUDIT. I don't know if
qdoits?
it's
I think those are multiple qubits, like tridits and quadits and so forth, are multiply linked to get quantum linked together qubits.
yeah,
Okay.
it had some layer of dimensionality. It sounded
I
like
haven't heard of that one, but this concept of building computers out of massive arrays of tiny little self-contained
Yeah, I mean,
things has been around for a while.
there
So
was the connection machine way back, and
right,
it'd
yeah,
be interesting to see what could be done with today's really small and fast single
yeah.
chips.
I first got involved with that concept with a thing called back in the day was they were called transputers. These are cool
Oh
little
yeah,
chips, and one of my projects was I ported the C compiler uh, to transputers so it could run off of a Macintosh.
yeah,
Transputers have 4 channels, so you can snap them together like Lego blocks with literally no other hardware. It's just like you could put 4 of them down on a board and they can immediately connect to each other.
yeah,
The downfall of that was those serial channels just weren't as fast as they should have been.
yeah. That kind of reminds me of the IBM, these 433 qubits modular into like 16,000 something by the end of next year. That's kind of what that reminds me of. Now, for everybody else, we haven't heard from the other two, which is fine. And you could post anything or any questions you have in the chat here. Is these things either fall under classical computing or quantum computing. Now, quantum computing uses quantum mechanics. It can do linear algebra, complex numbers. So that's why I harken back to the hybrids. Is basically, even if it's a hybrid neuromorphic computer, these types of things. It's just there's certain tasks that quantum computers are not good at. They won't likely be the brain ever. The memory will start to move into the computer itself, the quantum memory. But yeah, there's figure I open up a next laptop in 5 years, maybe CPU, GPU, and now a QPU. That's the total possibility, but that's where many people don't understand as far as like there's certain things that will always be better likely for classical, and then we've mentioned, or Ron's mentioned, the GPUs, and then now the QPUs, and the same thing with these articles I've been presenting, at least a couple of them, how to find ways to get quantum machine learning advantage. Because you don't want to just go at it. And especially my approach is in medical with FDA and finding out what would be needed to change in the FDA. So this is like IEC and ISO and NEMA in order for a start of any company to be approved for a submission for a quantum machine learning algorithm in the next years. So it moved really fast from say 2020. They were saying, oh, deep learning algorithms are not transparent. They're just opaque and they're not understandable, these types of things. I did a study last week, and at least two of the 10 were using deep learning. So that's encouraging too, because if you have quantum convolutional neural networks, you could see that progress that's been made in like 2 years, basically, with AI and ML, to not just having mostly locked algorithms to more of this, highly continuous learning. So the key is predicate device, right? It functions like it. Its technology is different, but at that same time, you're getting advantage from the quantum technology that's reliable for patient use. So it'll be interesting.
I'm sorry, that was one term I didn't understand, as predicate device.
Yeah, it's a pre-existing device that is similar to it. Now, there's all different levels. Like, say, for instance, if GE, three of the approvals for last week were GE. So their approval letters tend to be very short because they have all these predicate devices. The FDA knows who they are. Now, the ones that aren't quite well known, they'll go with all these charts. So you need to prove that it's, well, number one, that the probable benefit is greater than the probable risk of it all. Like quantum computing or quantum technologies in this specific case makes such a valid claim of helping instead of like the, whatever percent risk of harming. And then 510K approval is there hasn't been any de novo or PMAs this year. Now those two, a de novo is basically from scratch. It doesn't have a predicate device. As I said, in AI and ML, there's only been 510K approvals in 2022. So you best aim at something that, will be deemed as that. So the FDA, I don't think cares as much as about computing. They care more about long-term patient safety and you taking care of the medical part of it. It's like the ISO, NEMA, IEC that has these standards. So there was a big meeting in 2020, and I mentioned before, one of the previous speakers on this panel, he was part of that, and they put all these, pictures of Zooms of people up, and it was preliminary, 2020. But that was the ISO IEC. Now, IEEE standards, IEEE quantum standards, there's 9 of them. And, they get feedback from Quantum Economic Development Consortium, QEDC. But yeah, that's the thing. It's so the first level is the Maya, right? It's just a little bit change. Like if you were to come up with a shampoo that was just so different and radical than the current one, it's too much change. So that's why I say with quantum machine learning and transfer learning that's more likely, to start to gain traction with the FDA, because it's fine tuning something that they're already familiar with. And then the tricky part will be convincing the simulator and or the computer, the quantum computer, go through all these other checks, as far as, probable benefit. So.
Okay, thank you. So it's actually less about the technology than about validating it and incremental improvements.
Yeah, incremental improvements. I mean, the thing with, so the AI and ML in software as medical devices, there was a paper in 2020, and it was a call to action basically for the FDA to, I think what it was is just simply stating what all these devices going through were. And I don't know if it was an issue with just they couldn't keep up and basically say, this and this. So in October, so 2 months ago, last month, they announced kind of like a master list. And then I took the last 10 of those, and then 9 out of 10 of them are radiology. Only 1 is cardiovascular. 30% or 3 were GE healthcare related. And then 6 were based on primarily pre-existing images. That's why I've been, kind of focusing on that with stage 1. And then 2 were, 1 was like a portable MRI, 1 was a full 4D ultrasound. And then the other 2 were other types of image, I think segmentation, like more image computing. And then 1, I think, image reconstruction. So yeah, but it pays to do the research, because if you can keep looking at all these documents and find the consistencies, and I shared a slide on this one, you could check later on the deck, and it basically shows that, it's a different type of technology, but it doesn't pose any harm to the patient. Again, like you're trying to say that the minimal changes, i.e. now you're running parts on a quantum computer or simulator, and at that same time maintaining the like the essence of the previous. So say for like your transfer learning changing off of an original continuously learning algorithm that's been passed already. And that's what they have, these whole their charts, and they say, is it similar to the predicate device? And you literally like go through and check. And then sometimes you can use a reference standard too, like if it's not good enough just to have a pre-existing device that's similar to this predicate device. So it just depends, there's different types, but that's what it looks like, is basically the best chance for QML and FDA de novo, but there's no de novos this year. There's, I think, one or a couple last year. But it'll be interesting, right? Because somebody has to break the ground.
Yeah, thank you. I do appreciate that you wade through an awful amount of research to distill it down for us. And then even so, I have to cherry pick what is in kind of my wheelhouse to read of those papers.
Yeah, like I said, it's in the last deck, and then you can, if you get to the point of the approval letters, the first page and two are all FDA regulations that applies to everybody. So labeling and all this kind of stuff, and like the upkeep of your software medical device. And then usually it's the third or fourth page that gives like a good quarter page introduction, and then I distilled out of that, all the regulations. So, for instance, a portable MRI, and then like a 4D ultrasound, they average like 11 regulations that you have to meet between anything from sanitary of the instrument to the electrical part. They're just more complex than an algorithm. So.
So I'm wondering, I mean, given the current state of medical approvals for durable medical equipment and diagnostic equipment, going through all that red tape just to get even a classical product on the market, is it going to be exponentially harder to get a quantum product on the market
Well, I think you just
and get those clearances?
I think you just need to meet the other regulatory body standards. Like
Yeah.
if you look at all of FDA standards, it's like basically upkeep in medical. And then they already have, so you'll see lots of ISOs and ASTMs and ANSI and all those types of things. I think the harder part is just, for the first one of those, because I don't think they accept IEEE. But say for instance, if IEEE and IEC meet, and then anyways, IEC and ISO met 2 years ago regarding quantum tech. I don't, not specifically for medical, but yeah, I think that'll be the harder thing, is basically meeting the regulation of whoever, and then they'll, like you said, likely take some years or whatever in order for FDA to feel comfortable, because it's patient safety that they're concerned about.
Yeah, it'll be interesting to see what actually pops up first.
Yeah, it will. And I would check out the IEEE quantum standards. So there's software, hardware, all that kind of stuff. There's a nice page on it. It basically saying the QEDC didn't ask them, but they had to talk or whatever. I forget the exact verbiage, but there's other kind of, there's basically what they put it, I'm going to explain it in a little spiel here, but basically they want to have it, so you can easily communicate between researchers, knowing your standards of your specific computer. And I'd say things are definitely have narrowed down between, say, the 5, in quantum hardware, and maybe a little bit more. But, that's the thing is, and then for them, they want standards for liability. So when a vendor and a researcher have talks or whatever, there needs to be standards. So, if you look at your laptop brick or something like that, and then, see who's on there, UL, NOM, all those types of things. But it's for the good, right? And I think, it'll first have to come with the rock solid, just the computer and all that kind of stuff. And then, it's going to take some while, to have it in medical after that too, or basically standards that are aimed towards medical applications with quantum. So, but that doesn't stop people from researching. IBM, Amgen, Roche, all these big papers, all of the COVID papers with QML.
So
yeah,
the quantum world appears to continue to move forward. Here's a little experiment that everybody in this group can try. I did this a day or two ago. Go to Amazon and search in just the books for quantum computing. And then once the thing pops up, sort it by publication date.
Oh, okay.
And this is an interesting little experiment. What I found when I did it a few days ago, the first 50 some books that pop up are pre-order. They're not even out yet. That's a very interesting metric. Can't hear you, Kevin.
Yeah, that's interesting. I thought you were going to say something else, but I've done other, trying to think of something productive that I did. But, 2021 was a huge year for partnerships. And then to a certain extent, it was, it was big. And then people were projecting for 2023 to be huge. And now we say National Science Foundation, practical quantum computer. And then I still want to investigate more with the Dell INQ, because when that first came out, it's an enterprise solution and it has quantum technologies. So I don't think there's really too many other hardware manufacturers that can make that claim. And then this ion trap technology, especially Quantinium and IonQ, they're in nature all the time. And it's not just fundamental research, it's for some application that they're inherently limited by qubits and noise anyway, but that's what people are experimenting with. And like I said before, you could have multiple scenarios where you're using gate-based superconducting qubits for this specific things, and say you need the versatility with IonQ or Quantinium for other things too. So it's interesting, but I kind of see it narrowing down a little bit as far as, we still have photonics and spin qubits and neutral atom, and it's just any of those could break through too. Now, are you familiar with that? Anybody, as far as those three, are they gate based, or because I've only seen recent research on that? Because most people say, okay, yeah, we need a gate based quantum computer.
I'm not sure about any of those that are mentioned, but there is another tack which might be more in the research realm, which is using quantum itself. And the buzzword there to look for would be the quantum annealing.
Yeah, I know for sure that one's not gate based. They always say that's the opposite of it, but I've heard other people say, as far as, I don't know if you can directly substitute a circuit on photonics or spin qubits or neutral atom. So,
well, the trapped ions, I'm pretty sure, are classified as gate based, because they have some better features as far as connectivity, but it's still getting a pair of qubits to interact with each other.
right.
And, that's basically a gate. And again, in quantum, there are no such thing as physical gates. These are unfortunate terms that just mean a time-sensitive operation is going on, exchange of information between two or more qubits, or one or more qubits, or in some cases 2 qubits.
Yeah, to speak to Ron's point, conceptually, there's these different layers, and at the level of gates and above, if you design an algorithm at that higher level, it could run on any particular hardware that implements those gates in hardware, even though the actual layers between that gate abstraction and the hardware, there's still several layers of abstraction. But most of the algorithm research as opposed to quantum error correction and so forth, is at this higher gate level or above, and so would run on anything, whether it was photonic or superconducting or ion.
Yeah, I was surprised to find in the IBM world, if you follow the Qiskit channel, um, the there's the Qiskit language, there's the Q assembly language. There's actually 3 layers of stuff that goes on below that in the to get Quasum code to run on the IBM hardware. And this has to do with gate placement, gate swapping, routing, mapping to the double hexagraph topology and all that stuff. It's like 3 layers of stuff that you don't hear about. So that particular program will run from an abstract mode in assembly, which is lower than a high level quantum language
Yeah,
on the IBM stuff, and then only on the IBM stuff.
And
So it's crazy.
was anybody on that call? So it's basically, I think it was one of Helen's. And, it was all about error correction and all these, like, they kept saying it's just like, and we swap and we do this because we have quantum error. And I said, well, how does all this translate to the future? And I'm sure you've learned things from it, but basically there's lots of things that are implemented into quantum circuits just to account for error. And
At that level, it's error mitigation. Error correction in quantum, the quantum concept and error correction, they don't get along. So serving error is through mitigation, where you're doing things like you're looking at things in the program that are going to be noisy, and you can swap them around a little bit into configurations that are less noisy. So that's how you mitigate error.
yeah.
You change the circuit from one that is bad to one that is better.
Well, I guess some interesting news. So Quantinuum, they've kind of switched over to the Pacific, or that they have new partners out there. I'm not quite sure. There's all these different contracts going on. And then the other stuff is like, people follow IBM gate-based, and there's still Rigetti and Google. So Google's the dark horse because they come out with all this QML papers, although the hardware, I think the last one has been quantum supremacy. But it's just interesting because, like, how will all this, say, what is the degree of the dynamic decoupling, the error mitigation that IBM just announced? Because I think most people agree, don't go higher in qubits unless you fix the error. So it has to be good to some extent, is the assumption there.
Yeah. Well, there was at the Washington, D.C. group, Helen, I forget the name of the lady. She put a presentation on regarding error mitigation in the IBM world, and her entire world was one layer of the compiler, and to the point that she wasn't really even cognizant of what goes on above her or below her. But her layer was error mitigation, and its whole job was to again rearrange the circuit from known bad noisy configurations to better or configurations with better noise profiles. And I mean, and this is her PhD study work, and she is completely engulfed in it, and she's just one tiny little bit of the stack.
Yeah.
So that tells you how much this error thing is a big thing.
Yeah, because I don't see gate-based superconducting go anywhere just because there's so much money. IBM's putting $20 billion. This is part of Chips and Science Act to keep the manufacturing inside the U.S. And they have the president of the United States, Joe Biden, with the CEO of IBM staring at a quantum computer with an American flag in the background. So if that doesn't, as far as tell you the level of commitment and quantum computing. So most people don't know this, especially quantum investors. Quantum computing is a government initiative. So back in the early 1980s, NSF was first to fund. And anywhere from today, there's 21 government institutes, organizations supporting quantum, from Air Force Research Lab, DOE, DARPA, and especially NSF with this projection for the next one for next year. So yeah, I think a lot's ahead of us. So does anybody else have any other questions before we wrap up here? I appreciate everybody coming on. So obviously in the US, it's a big holiday tomorrow. And then I'm kind of wrapping up this, and then I got a bunch of other work to do. But yeah, it's good to see everybody and returning people and the new guests with Mary and the other gentleman on too. Thank you for coming on. Any other last comments?
I'm in talks with Helen to do a presentation for her group in maybe February, so stay tuned.
Yeah, so you can, they're all over the place. I think Toronto, Washington, DC, to take a look. I get those updates too, so I'll check it out. And then, so obviously, okay. So without getting further in depth into it, it sounds good. if I can make it. Thanks everybody. So this is,
Thanks, Kevin.
Yeah.
Thank you.
yeah, I appreciate all the feedback. November 3rd, 2022. Take care, everybody.